Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. So today we are going to discuss about the next chapter in this course, which is frequency response technique. So in the previous lecture, we already discussed in details about time response technique, which is we use root locus as tools to analyze the performance of the system. So in this chapter, we will use the frequency technique, and then we use word plot as a tool to analyze the performance of the systems. Before we go further to discuss about this chapter, let us look at what the outcome that you will get from this chapter. So at the end of this chapter, you should be able to understand the concept of frequency response. For frequency response analysis, so we can use either bot plot or Nyquist. That is a basic plot that we can use to analyze the performance of the system. So in this course, we will only focus on bot plot, where you will learn how to draw the bot plot by using asymptotic approximation technique. So that's mean we draw the board plot based on approximate drawings. Next, you will also learn how to draw the approximate board plot based on first order and second order system. Okay, for second order system, so you will learn how to do the correction to the plot that you have draw. After complete this board plot drawing, so you will learn how to analyze the system based on that board plot and to check the stability and by obtain the phase margin and gain margin. As an introduction, this technique, Nyquist and Bott plot, was developed by Nyquist and Bott in 1932 and 1945 respectively. So this is considered as a old technique that was come first before root locus technique that was developed by Evans in 1948, where this technique have several advantage. First, from the data that we get from experiments, so we can model the system and we can do the modeling and to find the the mathematical model of the system, and from that physical data. And also, this frequency domain analysis help to determine the absolute and relative stability of the closed loop system. And this frequency domain analysis also can be extended for analyzing and designing nonlinear control system. Besides, from this technique also we can determine the stability of the system. The concept of frequency response. So let's say we have this system. This is the system with mass, spring, and viscous damper. So in frequency response analysis, the input to the control system is fed with sinusoidal signal with different frequency. The output, this one, from the time invariant system will be the same sinusoidal signal with same input frequency, but variation in magnitude and phase. So the change in the magnitude of the input signal and phase for a wide band of input frequency can be determined by using frequency domain analysis. This output response can be plotted in a several way. So two of them is by using function of frequency with separate magnitude and phase plot. This technique we call plot plot technique, where the magnitude of this plot is in decibel versus log omega, which is velocity of frequency, where dB is equal to 20 log magnitude. The phase curve is plotted as a phase angle versus log omega, which is the same. Omega is equal to velocity of frequency, which is in radian per second. Second method that we can use is by using polar plot. So where the phasor length is the magnitude and the phasor angle is the phase. As earlier mentioned, so in this topic, we will only focus on this technique. Asymptotic approximation plot. The log magnitude and phase frequency response curves as response of log omega are called Bode plot or Bode diagram. Consider the following transfer function: Gs equal to Ks plus Z1 times S plus Z2 till S plus Zk divided by S power of m time with s plus p1, p2 till pn. So from this transfer function, so we can find the magnitude frequency response by change this s with j omega for all term inside this equation, so that this equation become j omega plus k. This one s we can change to j omega, and also this all s inside this equation. So the process can be simplified by converting into dB. So that's mean we just change this into decibel, and the algebraic sum would yield the total response in dB. So how we can do that? So from these equations, so the total magnitude response is equal to zero terms magnitude, and we refer to this one zero terms minus this whole terms magnitude, where in order to do that, so we have to convert all this into decimal. In order to convert into decimal, so we have to use this formula, 20 log magnitude for j omega. Okay, so to solve this one, so for k, so we just put 20 log k plus 20 log magnitude of this term, and then plus magnitude of this term, and then also same plus 20 log magnitude of the next term till at the end of this zeros term. For this part, we just minus 20 log j omega, this one, j omega power of m, and magnitude for this one, minus magnitude for this one, minus magnitude for this one till n. Next, the total phase frequency response is the sum of phase frequency response curves of zero terms minus the sum of the phase frequency response curves of the whole terms. Straight line approximation can be used for individual magnitude and phase response to simplify graphical representation of overall system. This figure shows the example of frequency response, which is consists of this magnitude plot and frequency of phase plot. This is magnitude and phase response for the system with GS equal to 1 over S plus 2. Okay, let us look at how we can plot the word plot. So for example, we have a system with GS equal to S plus A. So in order to plot this, first we have to change this S with j omega. So after we change, we get this S become j omega plus A. And then we have to rearrange this equation until we get this value A become equal to 1. So in order to do that, so we just put this A outside this bracket, and then we just time all this with A, and then when this 1 time with this A equal to 1, when this part time with this A become j omega. So that means this equation is equal to this equation. So why we have to do like this, and because we want to identify the cutoff frequency for this system. Okay, based on this equation, so at low frequency, when omega approach to 0, so that means when we put this omega equal to 0, so the equation become j omega equal to A, because when we put here equal to 0, so this one becomes 0, 0 plus 1 is equal to 1, 1 times A is equal to A. The formula for magnitude response in dB is 20 log m. In this case, m is equal to A, and or j omega here. So we just put A here. So that means the equation become 20 log A. Okay, at high frequency where this omega is very big compared to A, so the equation become, ignore this value of 1, so the equation become A j omega divided by A. For phase response, when this value is equal to 0, so we can calculate by using this formula, where to calculate the phase is we use shift tangent, this imaginary part omega divide by this real part 0. So when this omega divide by 0, this one become infinity. So shift tangent infinity become 90 degree, and that's why we get this one 90 degree. So the magnitude response in dB become 20 log A, which is refer to the low frequency of this response, plus 20 log omega over A, which is referred to this is referred to high frequency for this response. And then we can simplify this equation become 20 log omega. So if we plot dB 20 log m's against log omega, gj omega become a straight line. This is the board plot that we can draw based on the derivation that we have done. So as you can see in this derivation, the cutoff value at lower frequency is at A. So that means this value of A, which is referred to this frequency in radian per second, is considered as a cutoff frequency for this magnitude plot. The board plot start with this 20 log A. At this cutoff frequency, this plot will going up with slope 20 dB per get, which is depend on this equation at 20 log omega over A. That means this line is referred to this equation omega, which is depends on the value of omega, which is start from 0 point something till infinity. Next, for phase plot, so the cutoff point will start one decade before this A, which is at 0.1 A, and then end one decade after this A, which is at 10 A. So this slope will be 45 degree per decade, where the cutoff at high frequency is at 10 A, which is equal to 90 degree. So based on this equation, so we can draw start from 0 degree, this phase plot will increase with slope 45 degree per decade till 10A, which is at 90 degree, and this plot will maintain at this 90 degree. This graph show the difference between the asymptotic explanation plot with the actual plot. So as you can see in this difference, so there is around 3 dB difference at this cutoff frequency. As you can see, at this cutoff frequency, the value for this asymptotic approximation is at 0 dB, while for this actual results come from simulations, so the value is at around 3 dB. Also same for this phase plot. So this blue one is referred to the asymptotic approximation, and this black one is referred to the result based on simulation. So there is a difference at the cutoff frequency, where cutoff frequency occurs at this point, which is not 0 degree, which is around 7 degree, and end at around 83 degree. Next, if the GS denominator, for example, GS equal to 1 over S plus A, so based on this transformation, we can rearrange like this because we want to make sure this part is equal to 1, and from here we can confirm this A is represent the cutoff frequency. At low frequency, so we just put this value of S here, because S is equal to j omega. So we just put this value omega equal to 0. So that means this one equal to 0. So when this one is equal to 0, so the equation of GS become 1 over A. To find the magnitude, we just put 20 log 1 over A. Next, at high frequency, we just change this as here with infinity. So when this part is infinity, so this 1 can be ignored. So the equation become 1 over A times j omega over A. Okay. When omega is equal to 0, so this equation become infinity. And when this omega is equal to infinity, so this equation become 0. Okay. For the phase, the same technique that we have discussed before can be used. But in this case, the component is located at this denominator, so that's why the result become negative here. So the overall equation to represent this equation for both plot is 20 log 1 over A minus 20 log omega over A. Okay, this negative is because this component is denominator. This result is similar with S plus A, except the slope is negative rather than positive. Also same for first plot, the result become negative of the previous example since the function is the inverse. This is the final result that we get. So as you can see here, the cutoff frequency occurs at 1. Both plot decrease with slope negative 20 dB. For the phase, also same. This starting point is at 0 degree. Slope is 1 decade before 1, so which is at 0.1, and at 1 decade after, so which is at 10, with value negative 90 degree. For the case of GS equal to S and GS equal to 1 over S, we can draw the both magnitude and phase like this. For GS equal to S, we just change this S to J omega. And then based on this, the magnitude is G J omega equal to 20 log omega. So in order to draw this line, we just put any value for omega as long as the value is not equal to 0. So we just put the small value first. So for example, we put 0.1 here. So if we put 0.1, so the result become negative 20. So that's mean at this 0.1, so the magnitude is at negative 20. And when we put this one is equal to 1, that's mean 1 decade after. So this equation become 0 time with 20. So the result become 0. So that's mean when 1 radian per second, magnitude is equal to 0 dB. And next, based on these two results, so we can simply draw this line that represent this J omega. For phase, in order to find the phase, we just use tangent, shift tangent, imaginary part, divide by real part. In this case, we only have J omega, and that means without real part. So our real part is equal to 0. So that's why we just put here omega divided by 0. So when omega divided by 0, this one become infinity. So shift tangent infinity become 90 degree. And that's why we get this result like this. The plot for this phase start with at positive 90 degree. Next, for the system with GS equal to 1 over S. So same, we just change this S with J omega. So from here, we can find the magnitude for this system become 20 log 1 over omega. 1 over omega means omega power of negative 1. So when we put this value omega equal to 0.1, so log 1 over 0.1 is equal to log 10. Log 10 is equal to 1. So when this part is equal to 1, so that means the magnitude for this GG omega become 20. So that's why when the frequency at 0.1 radian per second, so the value for magnitude is at 20 dB. Next, when this value is equal to log 1 become 0, so that's why we get this value become 0. When 1 radian per second, the value for this magnitude become 0 dB. And after we get these 2 points, so we just draw these straight lines, which is represent the magnitude plot for this equation. So the plot that we draw is referred to slope 20 dB per decade. Next, for phase, so we use the same formula as here, but in this case we have to put negative because this equation refer to 1 over J omega, and that means J omega is located at this denominator. So when located at denominator, so that means this part will minus this part. So that's why we put this one minus. And also omega divided by 0. So when omega divided by 0, this one become infinity. And that's why we get this one is equal to negative 90 degree. Based on this calculation, the phase plot for this equation become fixed at negative 90 degree.